Hello everyone, I'm Irene. Welcome back to our openEuler tutorials, OECA series course. Today I'm going to introduce openEuler users and groups. Over the next half an hour, I'll show you exactly how to create and manage user accounts securely, master group permissions for team collaboration, control the file access, and use privilege escalation safely. Whether you are a junior admin or brushing up on fundamentals, these skills are essential for any openEuler professional. Okay, let's dive in. Alright, picture this. We are part of a team that manages a bunch of servers. Now, should everyone on the team get full admin rights? Definitely not. First off, not all data should be visible to every admin. And second, if someone on the operations team isn't comfortable with Linux, and we give him full admin access, well, that could end really badly. That's why, especially when security is a big deal, we need to set up clear user roles and rules for how people should interact with the server. Linux is a multi-user, multitasking operating system. Basically, that means multiple people can log in and do different things at the same time without stepping on each other's toes. Let's say we have a Linux server with 4 users: the root, www, FTP, and MySQL. The root user might be checking system logs or doing some overall system maintenance. Meanwhile, the www user is tweaking the web app. The FTP user is uploading files, and the MySQL user is running SQL queries. They are all doing their own things, and nobody's getting in anyone else's way. In Linux, every user is assigned a unique number, not a username, which is called UID, user identifier. The system uses UIDs to identify users. Let's see the mapping between UIDs and user types. First, UID 0 is for the root user, the most powerful user. It can modify or delete any file and execute any command, so use it with extreme caution. Then UIDs 1000 to 60,000 are for normal users that can access and modify files only in their own directories, and read or execute only authorized system files. Lastly, UIDs 1 to 999 are assigned to system users associated with the services and background processes. No interactive logging is required for a system user, so UIDs help the operating system enforce security by defining what each user can and cannot do. Seeing these UIDs categories is great, but how do we check them in practice? To check UIDs, we use the ID command. If no option is added, it shows your current UID, primary group, and all group memberships. You can customize the output, for example, show just the UID with the -u option, or list all groups with the -g uppercase option. There are also options to display names instead of IDs, or to focus on real or effective IDs. Remember, UIDs define privileges, and the ID command helps you inspect them quickly. In Linux, every normal user account consists of 3 key elements: the username, password, and home directory. But there are also special accounts, like the root user, which has full administrative privileges. You can manage users entirely through the command line interface, including creating accounts, modifying settings, or even deleting accounts. Behind the scenes, Linux stores user data in critical system files. The extra password file contains basic account information. The extra shadow file holds encrypted passwords, and the extra group file defines all user groups. Config files like extra default user add and extra login.defs control default settings for new users, while the extra scale file provides template files for new home directories. These files work together to maintain user security and system integrity. These config files do the heavy lifting, but we manage them through simple commands. Let's examine some commonly used user management commands. First, the user add command is used to create new user accounts in Linux, storing information in the extra password file. The basic syntax of this command is user add space options space username. Some key options include the -u to set a specific UID, the -g to assign a primary group, -d to specify a custom home directory, and -s to set the default shell. To create a user with a custom UID and home directory, you can use, for example, user add space -u space 1501 space -d space /home/John space John. You can explore furthermore with these options. When you need to modify an existing user account, the usermod command is the tool for the job. The basic syntax of this command is usermod space options space username. For example, to rename John to James and update the home directory, use usermod space -l space James space -d space /home /James John. The usermod command is essential for account maintenance. The use of some key options are also listed on the slide. When it's time to remove a user account, we use the userdel command. This not only deletes the user, but also cleans up their associated files by modifying system account files. The basic syntax is straightforward. Userdel space options space username. The key options are listed on the slide also. For example, to completely remove user John along with the home directory, use userdel space -r space John. Use the -f flag with caution, as forcing deletion of a logged-in user can cause system issues. The password command allows users to change their passwords, while administrators can manage password policies system-wide. The basic syntax of this command is password space options space username. The key options are also listed on the slide. For example, to enforce password changes every 90 days with a 7-day warning, use password space -x space 90 space -w space 7 space username. Remember, the root user can change any password, while normal users can only change their own. Alright, let's talk about groups in Linux. Think of groups like clubs or teams. Instead of dealing with every single user one by one, we can manage the whole group at once. Assume that you've got 100 developers who all need access to the same project files. You could set up permissions for each person individually, but that could take forever, right? That's where groups save the day. Here's what makes groups special. Every group gets its own ID number. We call this GID. Each user has their own personal primary group. Everyone in a group automatically gets access to that group's files. It's like giving everyone on your team the same key card, way easier than making 100 separate keys. This is how Linux keeps permissions organized without driving system admins crazy. Just like users have UIDs, groups have their own ID system. Now let's talk about GID, the group version of UIDs. Just like every user has a unique ID number, every group has its own GID to keep things organized. Here's how it works. When you create a new user, the system automatically makes a matching group with the same name and number. GID 0 is special, indicating the root group, just like UID is for the root user. Those low-numbered GIDs from 100 to 999 are reserved for system groups that work at the background. You can use the ID command to query the GID. Just run ID space option space username. It will show you the group IDs. So GIDs tell the system who's in what group. Let me further explain the relationships between users and groups in a system. It's like being part of a sports team and some hobby clubs at the same time. The first rule is that everyone has to be on at least one team, which is called the primary group. It's like your home base in Linux. But here's the cool part. Just like you might play soccer and be in a book club, a user can belong to multiple groups at the same time. This gives you flexible access to different resources. Groups exist to solve a big problem. Instead of setting permissions for 100 users individually, we can just say everyone in the developers group gets access to this folder. Done. When you try to access a file, the system checks two things: your permissions and your group permissions. This two-layer check is what keeps the system both secure and manageable. Think of it like needing both a company ID badge and department clearance to access certain areas. Imagine you are running a company that's growing fast. At first, you might manage everyone individually, but as you hire more people, that quickly becomes a nightmare, both for you and for security. That's why Linux uses groups. Groups are our lifesaver when dealing with lots of users. Instead of setting permissions one by one, we can create groups for different roles, set permissions just once for the whole group, and easily add or remove users as needed. The command line interface gives us powerful tools to create new groups, modify existing groups, and manage who belongs where. That means adding and removing users. This isn't just about convenience, it's crucial for security. Proper group management means users only access what they should, keeping the system safe as it grows. Alright, let's create some groups. The group add command is like our user group factory. It sets up new groups and registers them in the system. The basic command syntax is group add space options space group name. But we've got some useful options to customize our groups. Details are listed on the slide. For example, to create a developers group with the specific ID, just run group add space -g space 5001 space developers. Then you will have a developers group with GID 5001. Here's the pro tip. System groups get those low-numbered IDs we talked about earlier. Normal groups get higher numbers automatically. When it comes to modifying groups, we use the group mod command. This command can rename groups or change their ID numbers. The basic command syntax is group mod space options space group name. There are also some useful options as listed on the slide. The one that I want to stress is the -o option, which allows groups to share IDs if needed, but use this carefully. It's like giving two teams the same number. Always double-check group changes because they affect the file permissions across the system. Sometimes we need to clean up old groups we are no longer using. That's where the group del command comes in. But there's one important rule. You can't delete a group that still has member users. To delete a group safely, first check for member users with ge10 space group name. Remove any users from the group. Then delete the group with group del space options space group name. The -f option forces deletion even if it's a primary group, but this may cause problems. So use it with extreme caution, only in emergencies. Managing group memberships is where the gpassword command is used. It can add users to a group or remove users from a group. The basic command structure is gpassword space option space group name. There are also a lot of useful options as listed in the slide. You can explore further to better grasp the use of this command. Let's see how openEuler manages user data. There are two critical files working together like a security team. Extra password, the user account information file, stores basic information like usernames, UIDs, and default shells. Every user gets one line with the fields separated by columns. But here's the catch. Because it's readable by everyone, passwords had to move. Then it comes the extra shadow, the encrypted user account file, commonly known as the shadow file. It contains encrypted passwords, hashes, not plain text, and tracks password expiration and lockout status. It is locked down with the strict permissions, readable only to the root user. So the password file says who you are, and the shadow file proves you are really you. While shadow handles passwords, the original password file still plays crucial roles. Here's some details of the extra password file, the system's user directory. Each line is like a user's ID card, with 7 columns of separated fields. Here's what they mean. Username, your login handle, password placeholder, now just X, the real password is moved to the shadow file. And UID, your user ID number, GID, your primary group ID. Remarks, optional user information like full name. Home directory, your personal workspace. Login shell, your command interface. Speaking of the shells, they are your gateway to the system. Some commonly used ones are listed on the slide. The extra shadow file is Linux Ultra Secure Vault for passwords. Unlike extra password, this file is tightly locked down with root access only. Passwords are encrypted and stored as unreadable hashes. It also tracks password expiration, lockouts, and aging. When the shadow file is enabled, the extra password file just shows an X where passwords used to be, like a C shadow file sign. Why this matters? Before shadow, that's during the 1970s to 1980s, passwords lived in the world-readable extra password file, a hacker stream. Shadow files were the security patch that saved Unix Linux authentication. In openEuler, Group management relies on two powerful files working together. Extra group, the group directory, which contains all group definitions, one per line, and manages membership and access control. It has the following key features. Every user has a primary group. That's their default team. A group can have multiple members, and users can join multiple groups simultaneously. Extra G Shadow, the group vault, which stores sensitive group security data, mirroring Extra Shadow's protection for groups, with access restricted to the root user or group admins only. Like user passwords migrated to shadow files, group credentials are moved to the G Shadow files to prevent unauthorized access to privileged group permissions. Let me walk you through the Extra G Shadow file. It's like the security control panel for your Linux groups. Each line has 8 sections separated by columns. First up, group name. Matches what you see in the regular group file. Encrypted password. This is where things get interesting. If it's empty, no password is needed. An exclamation mark means lockout. Last password change. When the password was last updated. Password validity period. How many days until it expires? Expiry warning period. How early to alert users? Grace period. Extra days after expiry before lockout. These controls are why important groups like sudo use G Shadow. It's the best defense against unauthorized access. Let's look at the etc. group file. It's like the phone book of group information on your Linux system. Each entry contains 4 simple but important fields, separated by columns. You can see the figure on the slide. Notice 3 key things. Most system groups don't list members here. They are defined elsewhere. The X means password data is stored securely in the Extra G Shadow. The format is consistent, always 4 fields, even if some are empty. Now let's look at the Extra G Shadow file. This is where Linux keeps the secure group information. Just like Extra Group, each line has 4 column separated fields, but with different security-focused data. Check details on the slide. The format may look similar, but this file controls who can modify groups. A quick security tip: if you see exclamation mark in the password field, that group is locked, and never edit this file directly. Always use commands like gpassword instead. Permissions are Linux gatekeeping system, as they control who can do what with every file and directory. There are 3 fundamental permissions you'll work with: read, write, and execute. These permissions follow 3 key rules. First, user hierarchy. Root has unlimited access. Owners get special privileges. Normal users have restricted access. Second, file attributes. Every file or directory has an owner user, an owner group, and specific permission settings. Third, access control. The system checks, are you the owner? Are you in the right group? What are your other permissions? For example, a file with permissions -rw-r, double hyphens, r double hyphens. It means owner can read and write, group members can read, others can only read. This 3-layer check is what keeps Linux both flexible and secure. Well, enough theory. Let's decode what these permissions actually look like in a terminal. Let's break down what we are seeing in this ls -l output. Look at this example. drwx6 dot to root 16384 June 6 15 24 lost plus found. In a permission string, drwx6 hyphens. The first character D means a directory, not a file. The next 3 rwx means the root user can read contents, create, delete files here, and enter the directory. The 6 hyphens means no access for a group or others. In other fields, 2 means number of hard links. The first root indicates the owner user, the second root indicates the owner group. 16384 indicates the size in bytes. The timestamp indicates the time when last modified. Lost plus found is the directory name. Those hyphen matters. Each hyphen represents a missing permission, in this case, locking out everyone except root. Let's decode Linux permission system. It's actually beautifully organized. Every file and directory has 9 permission bits arranged in 3 groups of 3. Owner permissions, what you can do. Group permissions, what your team can do. Other permissions, what everyone else can do. Take this example, rw-space, r-space, r-. Reading left to right. First triple rw-. R means owner can read. W means owner can write. Hyphen means missing X, owner can't execute. Second triplet, R double hyphens. Just R means group members get the read-only permission. The third triplet are double hyphens. Same for others, read but no modifications. See the pattern? The hyphens are like off switches for permissions. There are 4 key commands for managing permissions. You can check for details in examples listed on the slide. Basically, they are used to change permissions, change owners and groups, and set default permissions. When you need to do system admin work, regular user accounts just won't cut it. Linux gives us 3 ways to level up our privileges. Let's focus on the first 2. The su command. Basic form. Type su, enter root password. Then you become root, but keep your own environment. The su- command, that hyphen matters. So type su space hyphen, then the root password. This gives you a fresh root environment. Why it's better? Because it loads the root's path and profile, just like logging in directly. Remember that little hyphen makes a big difference in how commands behave. While su gets the job done, modern best practices point us to a safer alternative. That's a sudo space hyphen, the safer, smarter way to get root privileges. Unlike su, sudo lets you run individual commands as root without fully logging. It's the gold standard that gives just enough power for the task without unnecessary risk. There is an example on the slide demonstrating how it works. Just pause the video and check for more details. Well, so far, congratulations! You've now mastered openEuler's user and group permission systems. These skills separate casual users from professional system administrators. To take the next step, practice these commands in a text environment and explore further for advanced configurations. Hit subscribe for more tutorials and let me know in the comments what topics we should cover next. Thanks for watching.